Welcome to the course on modern digital communication techniques. This is the first lecture, and in the introductory lecture I have given you an overview of the syllabus. So we do not cover it again in this particular lecture, but we slowly go into the details of digital communications. We will begin with some of the basic tenets and how do we start looking at systems. So what I would begin with is one of the important statements of a famous author and researcher and scientist in the domain of digital communications, that is Robert Gallagher. And what he said is effective communication is fundamental to a civilized society. That's very, very important. So without communication we'd be led nowhere. We know this, so it is more of a necessity. And what we are going to explore in this particular course is the way to design a system for effective communication. Since you are taking this particular course on digital communications, we would assume that you have a prior knowledge about analog communications. So if we look at, or if we try to recall what you studied in analog communications, you would generally have a source, and we could say there is a source that is present, and from the source, this particular source could be generally a voice source. This particular source could be a video source, or could be any other kind of source that you are used to. So when you studied analog communications, you were generally concerned with analog sources, and mostly what you studied was some kind of a message requires to be put on to a carrier. Carrier means it carries, right? It carries. So when we say it takes on some, it's a carrier, what we say is that it has some attributes. What you have studied is the attributes of a typical carrier, or a carrier is typically a sinusoid wave. And in a sinusoid wave, you could write it is as a, let's put cosine omega c t plus some phase. So this is the typical expression which you are used to. And what you studied is that this feature, which is the amplitude, this is the frequency, and this is the phase. So we could say these are different features of the carrier. Now this carries your message, it carries the message, right? So it carries the message on these fundamental parameters by which the carrier is defined. So what you have studied is one could vary this amplitude, and what you would get is amplitude modulation. So that means, in other words, we are talking about modulation or modulating. That means you change this as per the original message. When you talk about this, you are talking about the frequency. You talk about frequency modulation. So generally when you talk about frequency modulation, you usually assume, or you consider that you are not going to touch the amplitude. This remains constant with time. This becomes a function of time. And the third is the phase modulation. So while you studied different ways of actually changing a carrier signal, it carries some message, you also studied the receivers, the different circuits by which one could demodulate an amplitude modulated signal, typically the envelope detector. Then you had the frequency discriminator for this frequency modulator, and phase matching for the phase demodulation purpose. So you could demodulate the signal and regenerate the message at the receiver. Generally this source is some real source, and here you generate the electrical signal. Similarly, at this point we are talking about the electrical message signal, and which again passes through some transducer to become the original message, example the speaker, if there is a voice over here, right. And typically our message, this electrical signal, could take a shape which is like this, a continuous variation, and the carrier, as you can clearly see over here, it's a carrier frequency with a much higher frequency compared to the speed at which the message varies. And when this is imposed onto this, if we talk about amplitude modulation, then you would apply some scaling factor with this so that it does not cause a reverse swing. Okay, you can still do it, but generally you would not allow the signal to go to the opposite phase within the modulation period, and you would limit the amount of modulation that is available, and your modulated signal would occupy some shape which is governed by this envelope, and it's not an exact picture, but you would have a modulated signal which would look like this, an amplitude modulated signal which is quite easy to draw. Now, when we go to the domain of digital communications, we are changing our perspective, and there are fundamental reasons why we should go to a digital communications, which will slowly evolve. But before we go into, let us look at what is the fundamental difference between this analog communication and a digital communication, and how do you transit into digital communications in as easy steps as possible, so that at least you are able to visualize. And what I want to convey to you is that all your understanding of analog communications would come and help you in realizing digital communication systems. You will, once you get into the domain of digital, when you go into the details, modules and parts of it, you would require a way of expressing them that will slowly evolve with time. So now, instead of using this particular signal as we have drawn over here, the difference that you get is the source is no longer analog, but you have a digital source. That's one of the important changes. Now, when we say it's a digital source, what we mean is that this continuous wave gets converted to some digital signal at some point. There are methods of doing it, and in this particular course we will go through those particular ways of converting this analog signal to digital and how do we move forward. But assuming at this point that there is some device which converts it to digital, we'll take a bit laymanish view so that things are easier for us now. So we say there's a digital source. By this we mean that it takes discrete amplitude values. So if this is the amplitude scale, and if this is the time scale, we would say that if this is the time scale and if this is the amplitude scale, we say it doesn't take a continuum set of values, it takes discrete values. And in time unit, it's going to take these values at discrete units of time. That means suppose I take this particular picture and I draw it here. It may not be exact, but it's somewhat similar to what we have. So what we'll do to convert it to digital, let's say in this time instant, I would choose the value which is given by this. In this time period, at this instant of time, I would choose this particular value. In this instant of time, I would choose, since it is above this threshold, I would choose here. So roughly speaking, very roughly speaking, if I were to sample here, I would get a better resolution picture. I could say that I have message which is almost like the one that I have drawn. What I'm trying to emphasize at this point is that it is taking discrete values, right? And the wave shape looks similar, only it is discrete. Now, there are several advantages of going digital, and the advantages will come clear as we progress into this particular domain. But this is one way of differentiating between the analog signal and a digital signal. Now, when do we have digital sources? Very simple situation. If you are thinking of sending an image. Now, if you look at today's sources, you usually use a camera which is digital. If you use a voice recorder, generally you have the voice recorder in your phone or any other voice recording device. Generally they convert it into digital domain. And if you are thinking of videos, you also have digital video cameras. So finally all these sources, they generate digital signal. Now, you are well aware that when you look into these voice sources, these .amr or .mp3 files, or you look into .mpg or you look into .jpg files, inside finally they are zeros and ones without even understanding analog to digital communications. This part you are very well accustomed to. So, if I ask you now that you send these files across from a transmitter to the receiver using your knowledge of analog communications, what you are going to do? The answer is simple, very, very simple answer. Getting motivated by the analogy that we have got over here of converting analog to digital, what we can think of is, suppose I have a sequence of zeros and ones in my files. Some random sequence of zeros, some random sequence of ones, and so on and so forth. Now, once we have this, what we can simply do is I read it off as a 0 and I read it off as a 1, and I associate this 0 with one particular amplitude level. Let's say 0 is here, this indicates a 0, and this indicates a 1. And I would know that I have to send these zeros and ones over a certain finite duration of time. And when I say that I would send it over a finite duration of time, I would restrict 0 to within a certain particular duration, and I would restrict 1 to a certain particular duration. This particular duration of time which is fixed is usually known as the bit duration in the current context, or it will be extended to the definition of symbol duration in the appropriate context. So, as of now, since we are talking about 1 bit every time being sent, I would say that the symbol is made up of 1 bit. So, what we are going to do is our source will convert it into some source which will keep on generating a 0, a 1, a 0, another 0, another 1, another 1, another 1, another 1, another 0, right, and so on and so forth. So, this particular waveform which is being sent would represent the sequence of zeros and ones that were stored originally in the file. Now, if you have studied analog communication, we can simply say that this particular sequence is my message, and this message I will use to modulate the carrier. Now, when I modulate the carrier, I could go back and say that I could modulate the amplitude, I could modulate the frequency, I could modulate the phase. Instead of having a continuous waveform, now I will simply say my input waveform is as simple as this particular shape. If you would ask that what would be a similar continuous waveform, if we say that, I would say that, well, probably the continuous waveform I can imagine which is closest to this could look something like this. We can use the dotted shape rather, okay, like this. So, if my continuous input symbol was like this, so I would stress this point, because since we are transiting from analog to digital, I would say let us imagine that my source waveform was like this. Let us imagine, no harm in imagining this particular thing. 2, 3, 4, and so on, and I want to send this. Is this a big difficult thing? Not at all, because if I think of sending it over a carrier which has a representative picture like this, I would say I have generated something which is, I need to rescale it. That's it. And then it is just the earlier amplitude modulation that I could be using, and my new modulated signal would be like this. So this is no different than the amplitude shift keying. What it says is that you shift the amplitude from one level to another level. So that means if I choose between two amplitude levels and I send it, I actually see a digital communication waveform. Now, if nobody tells you that whether this waveform is generated, or if I would look at another very precise waveform, let's say I take the input waveform as this. I can still send this particular waveform through analog modulator, and I would get a signal which would look like this. So all I am trying to tell you is that you can still use your knowledge of analog communications and use it to transfer digital information, and it will become a digital communication system. So when your when your amplitude modulation receiver acts on this particular signal, it's going to generate the amplitude. It's going to generate the envelope of the amplitude, envelope of the carrier or the amplitude. It's going to generate this waveform. Now once you have generated this, you can reuse your earlier mapping, that if the signal level is here, I would consider a 0 has come. If the signal level was there, I would consider 1 has come. So going by this, I would say at this point I would set up a decision threshold. I would set up a decision threshold somewhere in between, and I would say whenever the signal is below this decision threshold, there is a 0 which has been received, and when the signal is above this decision threshold, a 1 is being received, a 0 is being received, a 1 is being received, a 1 is being received, a 1, a 1, a 0, and so on and so forth. Now once you have decided that this is the received signal, you can now save it in your computer or in your phone and again regenerate it, and it becomes the image which was stored originally in your computer or in your phone or in a special memory device, and it gets regenerated and projected onto the screen. Same goes with your MP3 or your MPEG files. So what I'm trying to simply demonstrate at this point is that your knowledge of analog communication could be used sufficiently towards establishing a digital communication system in a very initial format. Now when we do this particular thing, there could be several issues raised, several questions could come up. Why at all are we going for this digital? Now that will become slowly clear as we progress through this particular course. As you can see here, one of the interesting features is that this digital communication system, I have sent a sequence of 0, 1, 0, 0, 1, 1, 1, 1, 1 and so on, but here somehow I have received something else because of some issue. So probably or what you can say that there has been an error into the system, right? If this was an analog communication system, what we are basically talking about is this particular waveform that we have here is now received in a little bit different way. So, as if my 1 has started to be generated at this point instead of this point. So, I have this 0 has been received as a 1, or sometimes we can say that we have missed out this particular 0 and instead we have read the next one. It is your interpretation, or you can say that 0 has become a 1 and one particular 1 has become a 0. So, as if the waveform has changed like this in this particular picture, right. In analog communications, this distortion is almost impossible to correct, because you do not know what is going on, you do not know what is the message, because this message is something which is generated at the source. If you knew the message which is to be sent, then you would not send the message. That means, if I know already what will be sent to me, what is the need to send that particular message? So, that means at the receiver we do not know the source message a priori. So, this particular mistake will not be captured and it will be used as it is in analog communication. However, in a digital communication system, we are having these sequences. So, when we have these sequences, the advantage of digital, one of the different advantages of digital communication system is that we can employ something known as forward error correction code. Well, in general, error correction code. You can use a forward error correction code, or you can use a reverse error correction code. Now, details of it again are not covered in this particular course, but time and again we will discuss little bits of it through which some things will be clarified. For instance, we can discuss very little bit as of now. We can say that let us form groups of 2 bits, or let us form groups of 4 bits. So, when we form groups of 4 bits, we are going to add one parity along with that. So, suppose my sequence is 0, 1, 0, 1 sequence, right. Suppose I have this sequence. When I say I want to have an odd parity, I am going to have one extra bit over here, which will be used to complete the parity to make it odd parity. So, as of now I have 2 1s. So, if I put one more 1, I am going to get 3 1s. So, I will know whenever I receive 5 bits 1, 2, 3, 4, 5, the sum of 1s should be odd. If it is not so, I will know there is an error in the system in that group of 5 bits. What we are going to do, the transmitter is going to ask the receiver, please send the bits again. Once the receiver sends the bits again and it checks the parity, if it finds the parity to be okay, it keeps these bits for saving or regeneration at the receiver. So, what I mean to say is that because we have converted to digital, we have the scope of adding a parity, right, and this leads us to put in error correction code. Which is a huge benefit. Why? The reason is you can now devise a mechanism, that means you can create system by which you can try to make errors as low as possible, and that is one of the fundamental tenets of digital communication. And this is because of the modern techniques of communications, and that is why we have this subject called modern digital communications, because there are so many new things into it. Of course, we are not going to go deeper into into error correction codes, but all I am trying to say at this point of time is that this particular technique is one unique advantage which motivates us to take up this kind of communication systems. Now, beyond this, if we look into it, since you have gone into the domain of digital, one of the things is that it's probably a bit easy to handle digital systems. It's a bit easier to handle digital sequences compared to analogs. The circuits are easier, and there's a huge amount of digital signal processor and processing capabilities already available. One of the simplest things is your computer. Your phone, which you carries huge amount of digital processing power. So, if you are using a digital system, you already have a huge amount of knowledge and you have a huge capability with you, which can be used towards making things better and better and better. Now, this is just one particular example that I pointed out. With time, you'll come to know many other details. So, one of the important things that we see is that digital is somehow become a natural phenomena as of now. Now, this doesn't restrict the use of analog communications. This doesn't render it useless, because finally these signals should go over these carriers, right? So, you need this carrier. So, all your knowledge of analog communications are necessary, because finally you need to build the transmitter front end, because let's say you have this source, the source is converted to, let's say, digital, right? Digital is converted to some waveform as explained here, right? Now, this waveform, it's still digital waveform if you look at it, or you can, well, if you are very, very restrictive, you can say, well, it is not digital, it's analog, but it's discrete in amplitude, it takes certain definite values, and then this diagram should change also a little bit. In the sense, I cannot draw this thing. I would draw in that case a picture which is this, followed by this, followed by this, another 0, let's say a 1, a 1, a 1 and a 1. This is the waveform that I should draw to make it appropriate. This is the time axis, this is the amplitude axis. Now, if I'm going to use real systems, we're going to have certain transition and there will be a certain amount of slope. So, making these idealistic assumptions that, well, this is digital, we have some waveform. Now, this is finally used to modulate your carrier as you typically do in analog communication system. At the receiver, the reverse process is followed over here, and once you are there, you are back into the domain of digital communications. So, what we are going to study is a huge amount of digital processing techniques, principles, design philosophies, which handle bits and convert them to waveforms and back from waveforms to bits in this particular course. So, from the next lecture onwards, we'll look at the ways by which you're going to visualize a digital communication system, so that you can categorize, break it down into smaller parts and start handling one unit at a time, so that finally you're able to design a complete digital communication system. Thank you.